So I've been working on electronic designs for more than 10 years now, mostly on wireless systems like 2.4 gigahertz sensors and readers, also on passive RFID systems, high-speed designs for e-book readers, multiple media controller, industry equipment. And in this presentation, I will show how you can take a microcontroller project from evaluation board up to a custom-made PCB step by step. Here in the component libraries and the rule set is a very important part, and also will give tips for placement and routing, soldering, and testing, and speak a bit about your optional features for a case housing. So the selection of your microcontroller is obviously a very important part. It deserves much consideration, and your choice does not so much depend on possible hardware features, but more on which microcontroller provides your favorite architecture design, of which architecture design do you want to be a part of. So you're looking into your favorite software, what you're comfortable to use, your compiler platform, and it makes a big difference if you find a lot of useful documentation and with an active community which provides examples for you, like Adafruit or Seed Studio, something like that. And also check whether your microcontroller choice is still actively available, because the availability reflects directly on the price. So going through available documentations will be actually the first step on what I call a modular approach. You choose a well-documented example, fairly similar to your own aim of your project idea, and start to reproduce this example exactly. And only once this example is actually functioning, you start to add something to it, extend it or replace it, and also only bit by bit, so in incremental steps. Only if one part actually works with the whole system, you can start and look into another part. And with this approach, you create your own verified schematics, blocks, verified footprints for your future projects. So microcontrollers and most peripherals are available as developer kits, or at least as breakout boards. You can plan your connections with software tools like twinSync.org. This is very helpful to create your basic setup and have actually a breadboard view for it, so you can connect it accordingly. And this might be already enough for a lot of projects, and you might want to stop actually here. But if you implement these things on your own custom PCB, you can enhance your project a lot. The learning curve for PCB design is actually very steep. You invest a bit of a time for getting the basics right, but any future project will be done in much less development time, much faster. Your design will be smaller, more elegant, it will fit in your custom housing, your target housing. The unit price will come down for production in quantities. You will get a higher performance as a side effect, because you will replace all those long wires in between any evaluation boards and breakout boards. And for the first prototype, it is good advice to stick with the components from your evaluation boards, but in different packages that are available from your distributor, from your production lines. And many component manufacturers provide you a lot of recommendations about how to implement their products. And if you can't find this in a data sheet, it will definitely be in an application note. Some manufacturers and production lines, like seed studios, provide their own component libraries. So you can download them and use them as a start, and then add your own libraries for the rest of the components. Again, follow the manufacturer guidelines, data sheets on this, and add as much information as possible in these library tables. Some tips for the schematic symbols: keep the pinout according to the top view of the component. It will help you a lot afterwards for testing and debugging. The footprint, you definitely verify the sizes in your library view, but it's very good advice to actually check the size in the final layout. Might be that there's some mirroring mistake or some scaling mistake. And a simple thing to add a 3D model, it doesn't take much time. It can be just a box with the correct height, but it will help you later to design a case or to show your PCB as in a picture. And also keep in mind the variables change very fast, and be prepared with alternative sources and paths. So this can also be added in the library table. And having all these informations in the library table means that your bill of materials sync with your changes in your design. So there will be no manual part in this process and less room for errors. So the schematics, trade your schematics according to your breadboard. Each function block on a different sheet, and every function sheet on the top sheet connected. And by establishing dedicated names for nets and buses, you do not have to trace every track from pin to pin and create an entanglement of lines which is hard to follow, but you have some kind of readability for your schematics. So the point is, avoid spaghetti traces like spaghetti code. Dedicated names will also be very helpful later for your routing, so we'll know which line you have on your pointer and how to route it. And if you have indeed a bit of an unverified peripheral you haven't used before, adding a zero-ohm SMD part in the signal line helps you to switch off this part of your system so it doesn't affect the other parts, to test it separately, and if it doesn't work, to still have the other parts available and functioning. This is also good advice for power functions, like you have your power coming from the USB, but somehow it doesn't work. It's very helpful to have a different power source, like a small connector for a different battery. For prototypes, test points, for all signals, can't hurt anything. Additional headers, especially for the programming signals, but also for any other critical signals, is very helpful. And there are two key points for a stable design. Make sure all power pins have separate decoupling capacitors, and the data sheet will specify the value, but it's usually 100 microfarads. And also look up the voltage level, power of ground for unused input-output pins. Don't leave them floating. So this is I think the very most important part of your layout design, establishing proper rules for your design. You should not even start with a single track before not checking with the PCB manufacturer and setting your rules right. First things, the layer stack. So 2 layers are often enough for a simple project, but with 4 layers you have the advantage to dedicate 2 complete layers for power planes. This helps a lot with power routing, So we can go directly from a power pad with a via to the right plane. This helps to get a more dense board and to have more space on top or bottom to shield actually the critical signals. To have a power plane on, a power floating plane on the top to shield critical signals, to improve signal integrity and reduce electromagnetic interferences. So the specifications for via sizes depend directly on your choice of layers. It will also be specified by the PCB manufacturer. It gives you guides on via sizes, on track widths and clearances. And the list of possible rule sets in your layout software is actually pretty long and might be confusing. But I think there are 5 points worth to have a closer look at. So, first, a bigger width for power signals wherever possible. A special value for the width for impedance critical signals. We have to calculate this for microsteps. Thermal relief for pads in planes, otherwise it will become impossible to solder, also heat up these pads for soldering. And at least for prototypes, silk screen clearings and pads, so silk screen does not overlap the pads. And if you're planning for a housing, it's good to include also your mechanical constraints, so the inner possible height in a case or space you need for fixtures. All this can be included in the rules. So one more thing is to be done before starting the layout. It's defining your board shape, and then you can import all the components on your layout view. I didn't say anything about the layout software, so I would recommend KiCad for private purposes and Altium for professional use, but there are many more out there. So when you import your components in your layout view, you have huge entanglements of all the nets and the buses connecting pins. But this soon untangle once you start rotating the components so the right pins face each other. And we start placing the components, so interface components first, like switches or LEDs, which are to be seen from outside, or antennas, connectors. And then choose a central place for the microcontroller and place the small decoupling capacitors very close by. And let's choose what critical signals need short connections to each other, so place those components close to each other. And it's also a good advice to leave some space between the components to be able to reach them with a testing probe. And with a good placement and fairly untangled connections, the manual routing is actually not that difficult. We start again with the critical signals, the high speed, the timing critical signals, impedance controlled antennas, and go through them to big power planes, power traces. The other power connection you can usually connect right down to your power plane. And also helps, sounds a bit difficult, but it helps a lot to keep one main direction of traces for each signal layer. Try to do it a bit to see it on the red one is the top layer, blue is the bottom. So it's a bit on the bottom, it's a bit from right to left, and top is more from the vertical direction. Otherwise, here on the 4-layer ones, the inner planes are not just for one power source. You can divide those planes into different power levels, or even build islands or thick traces that connect different power levels. Also, you can just write text in copper. It doesn't have to have a net name, or it doesn't have to be connected with a net. So the PCB production will surely appreciate to have numbers for each layer on the copper, and also your project name or project number. So the solder mask covers the copper tracks and leaves some clearance to the solder pads. It's usually green, and thus it's cheapest choice. And for prototypes or hand soldering projects, it's definitely a good choice because our eyes are sensitive to green. But there are lots of other colors available, and a pure white board or black board definitely looks cooler than a green one. To include the component designated silkscreen layer for prototypes is very important. It's important for easy location of components, so keeping the text, the silkscreen text, all readable in one direction is good advice. Also, keeping it consistent where to put the designator, so always left of pin 1 or always above pin 1 helps a lot to find your components. And the silkscreen layer is also a layer where you can include logos and graphics, definitely your name, your project name, and not to forget the version number. This is also a time where you should not forget to include any fixtures, wherever you have space in the edge or at the side of the board. Include some mounting holes where you later can just fix your board to something. It makes debugging, soldering much easier if it's not wobbling about. And what I very much like to do is round corners. Everybody who will later hold your PCB in his hands will definitely appreciate round corners. So when the PCB comes back from PCB manufacture, from production, first have to give it a good look, check for disalignment of solder mask and pads, or maybe shorts between the pads. And after that, prepare for the whole soldering. So clean the PCB, clean your surface, clean your mind, and start with soldering, mostly the most important part, the power part, and continue from there on, from complex to simpler parts, from bigger components, from smaller components to bigger components. But continue only after you really tested, not only power tested, but also function tested one section. If it works, then continue with soldering the other parts. So once the prototype is verified, it doesn't take much, it only takes a few more files to order higher board quantities and to get into automatic assembly. One thing is the panelization. It's not for the PCB manufacturer, it's actually for the assembly, so you have to know which machinery your assembly house is using. So you have to know the size of the panels, not only the maximum size, you have to know the exact size because they insert it into rails, it has to fit them. And once you have the size, you can leave for those tabs for the manufacturer to place, but if you have any overlapping parts, overlapping the edge of the board, make sure you place the tabs somewhere else, so it's not under your part. This will cause problems. The PCB manufacturer needs the board data as Gerber files, which includes the drill files, and the assembly house needs your pick-and-place files. Both can be exported from your layout software, and I recommend to check the exported Gerber files again with a dedicated Gerber view software, so that you see exactly the same data as the manufacturer sees your data. So lastly, there's the question how you present your PCB. We often used aluminum tube cases. These come in many different sizes, are very easy to assemble and disassemble with a few screws, and the PCB is very easy to insert and stable inside in some rails inside the case. The other advantage is the front covers can have custom-made cutouts or can be 3D printed, or can use a cardboard front cover for prototype and later let it be steel. If you're planning for some RF outdoor PCBs, so RF devices to use outdoor, then plastic enclosures or even 3D printed enclosures would be a better option. Or you may want to show your PCB just like it is, because it's definitely going to be beautiful and it's worth showing without a case anyway. So this is the end of my presentation. I will be around today, tomorrow also, so if anybody has some questions, I will be most happy to talk. And thank you very much.
Thank you. Thank you. Are there any questions for the speaker? Hi. Have you worked with any PCB manufacturers that ship to UAE?
No. I live in the UAE since 10 months now, so no, I have not had the opportunity. But I guess it's problematic to find the right one. Have you?
No. Any questions from the audience? And we have one more question from the slider. Brita, do you have recommendations for cybersecurity projects that require custom PCB designs, especially for beginners?
Recommendation, I guess, in terms of software. How do you understand this? So, yeah, as I said, so for PCB design software, which recommend KiCad.
Who asked the question? Maybe they can explain in what context they went in. Is the person? Sorry.
So maybe it's about the layout software, which I would recommend KiCad for, because I think I didn't actually mention it in my slides.
Okay, any more questions from the audience? Can I then just have one more big applause for Meriac?